Hi everyone, thanks for tuning in. And yes, this year it is a little bit different, but I hope you're enjoying the conference nonetheless. I am online right now, so please do use the chat function and we can make this as fun and interactive as we can. So, hello from Lockdown 4.0, or is it 5.0? I'm losing track. If you're in Melbourne, stay strong. We will come out of this on the other side much stronger than perhaps when we went in. So a quick introduction to those of you that don't know who I am from the Passive House Circles. My name is Kate Nason, and I'm one of the board directors at the Passive House Association in Australia. I'm also an architect with the ARVB down here in Victoria, and I'm now an environmental designer at Atelier 10. Of course, certified passive house designer and also Green Star accredited. But the thing that drives me really is my passion for the natural environment and how the built environment can really shape how we can protect it, really. And now, as a sustainability consultant, I get to work alongside architects to help make their aspirations of carbon neutrality on their projects not just a pipe dream, but a reality. So it's a really fun role to have. What we do at Atelier 10, just quickly, I work with a fantastic team and we push innovation in terms of sustainability, resiliency and health across all our projects. And of course, passive house consultancy is actually a very much a growing area of the services we offer, which is really exciting. And I just like to show this graph at the beginning of most of my presentations because it really sets the scene. This is why I'm so passionate about the passive house standard. We can tackle the operational emissions with this standard. The first 3 steps of the curve towards carbon neutral buildings is tackled with the passive house standard. We're talking about passive systems, we're talking about the envelope, we're talking about the equipment we use, it's all covered there. And only then, once we get that right, should we add renewables onto our buildings, and only then should we offset. Unfortunately, the trend is to offset immediately. That shouldn't necessarily be the first port of call, it should be the efficiency of the building. So I'm going to take you through where code sits on this curve and where passive house sits. So we think it's somewhere around here, but what is exactly the performance uplift that we're looking at if we want to take our projects from code to passive house? And where exactly is industry best practice at the moment? Yeah, we should define that as well. You know, should I even bother going down the passive house route? How much effort will it be? So what does it mean to go from code to passive house? We're going to unpack this question through a series of studies that we've conducted on multi-residential buildings. So we've had a lot of interest from clients to do passive house feasibility studies on their projects. So this isn't a study just on one project. This is an accumulative study that we've been exploring for quite some time, and I'm really excited to share some of the insights with you. Again, this is always a work in progress, and please do chat to me in the chat function because I'd love to hear your questions, and let's start a discussion about this. So first of all, our scope needs to be define the minimum code, which is 6 NatHER stars for residential buildings, and the industry best practice. Now, from our understanding and our observations, 7.5 NatHER stars is relatively good in terms of industry best practice, and that's what most of our clients for multi-res are aiming for. So what does it take to get from there to passive house, and what is this gap? So let's explore that together. So first, we need to define what the baseline is for this study, and we need to look at what that rating is and what that performance standard or performance outcome is. So we're looking at typical multi-residential buildings, as I say. We're looking at buildings that are roughly 5,000 to 15,000 square meters, mixed use residential with retail on the ground floor. It's a fairly standard formula for Resi down here in Melbourne anyway. I'm sure it is in Sydney and across Australia and probably the world. So unpacking this particular typology is quite interesting. First, we need to look at the form factor. The performance starts with the shape of the building. So the bigger the surface area to the volume, the harder the envelope will have to work. So we need to set ourselves up from the beginning for success. Unfortunately, we don't always have the opportunity to do that, not as, you know, sustainability consultants anyway, but as architects even. So we're often dictated by planning policies, neighborhood character, facade articulation, and sometimes we're just given a massing to begin with. So we need to deal with the cards we are dealt. So looking at this particular study, we're looking at a form factor of 0.4 to 0.8, just as a sort of a range. We're also looking at a typical business as usual materiality. So looking at a concrete structure with a steel stud envelope. So unpacking the baseline, we've modelled this particular typology of building in First Rate 5, which is the compliance software, and we've gotten results around about this, which looks pretty good. I mean, Passive House standard is down at 15 kilowatt hours per meter squared, and we're already seeing that, you know, 6-star is almost 30, which is the Passive House low energy standard, and 7.5 stars is almost at Passive House standard. So what? Well, yeah. What does this mean? And I think, yeah, it's important to have a look at this a little bit deeper. So we modelled the same building with PHPP, and we got these results. Why? And why are we actually bothering to model it in PHPP? Well, we always get asked this question. We always get asked the question of, how does NatHer stack up to Passive House? And it's such a difficult question to answer because it's really like comparing apples and oranges. The reason for this is, you know, those of you that use PHPP, this is nothing new, but I think for those of you that are on the line that might not be as familiar with the Passive House Planning Package, which is the software you use for compliance, you know, this is really important stuff to sort of understand. We're not comparing the same baseline, essentially. The compliance software doesn't really take into consideration variations in thermal mass, nor window quality, nor does it consider repeating thermal bridges in the envelope, nor does it consider air tightness, and nor does it consider linear thermal bridges. So I think that's the biggest reason why these graphs are so different, from Passive House in the blue to compliance software in the green. And so just as a base case, we've chosen concrete as our thermal mass. We've chosen a non-thermally broken window, which is sort of business as usual. We've chosen steel studs. We've chosen an air tightness of about 10, which is, again, sort of an average business as usual rate. And we've also chosen to not consider thermal bridging, because that is, it's quite uncommon for buildings to look at that when we're just going for code. So the step changes that define the pathway from code to Passive House. What are they? Step 1, and again, we've listed these not in the hierarchy of, say, performance uplift, but we've listed them in terms of what our clients have generally been more interested in. So step 1 is dealing with the fabric of the envelope and dealing with optimizing the base case. So how can we actually get from 6 to 7.5 NatHer stars? That's in step 1. Step 2 is dealing with the thermal performance of the envelope and looking at thermal bridges. Step 3 is looking at ventilation, and step 4 is looking at air tightness. So I'm going to walk you through these 3 steps for that business as usual base case building. So optimizing the base case first, What does it entail? It entails window to wall ratio. We need to look at the window performance, and we need to look at the envelope performance. And all of these are interrelated. So on a sliding scale, if you start with a really, terribly performing window, you're going to have to reduce the amount of windows in your envelope. So your window to wall ratio will reduce. And likewise, if you go for a better performing window, you can increase your window to wall ratio within reason. Again, this is achieving 7.5 NatHERS stars. So if you're looking at this graph going, oh my God, those figures are terrible. Well, just hold your horses. We will get to the passive house part. The other thing is the window system and the envelope performance are obviously very interrelated as well. So again, your wall R value is heavily reliant on your window system U value. So obviously the better one performs, the more, the less the other one has to compensate really. And this can have significant impacts on your GFA if your wall buildup has to get, deeper. So that's something to really consider. What are the performance impacts? Well, you can see that NatHERS, to get to NatHERS 7.5 star, just optimizing the window to wall ratio can save you 10% or thereabouts. Enhancing the glazing system increases your heating demand performance to 17%. And likewise with the wall R value, you can reduce it down to 21%. And these are some of the general figures that we've plugged in here. And this is using PHPP, remember, not the compliance software. So thermal bridging, what about those? So we'll tackle repeating thermal bridges first. So these are the thermal bridges that are within the envelope that are sort of a repeating stud in the wall build-up. And they're often out of sight, and not necessarily should they be out of mind. So what does the business as usual base case look like? Well, we've got steel studs with steel top hats, and that, will inevitably cause thermal bridging, which will cause energy loss, cold spots, condensation buildup, and mold. So those are some awesome things that you want to really avoid. And an easy way to avoid them is to just introduce another layer of insulation or some sort of thermally insulating material in between those two steel elements. Repeating thermal bridges can also be mitigated by the materiality of your studs. So looking at steel versus timber, timber performs much better, and you're going to have less issues with condensation, etc. And your wall performance will actually improve significantly even with the same buildup. Linear thermal bridges, now these are also really important because they're long ones. They're the ones that go all the way around the perimeter of your building, around the footings, around the roof to wall connections, around your balcony slabs. Really, really important. And again, will carry a lot of risk of condensation, cold spots, and energy loss. So if you mitigate them, and if I just flick back, I've got some very sort of indicative ways to do that, basically just breaking the thermal mass between inside and out. So looking at the performance impact of these linear thermal bridges, and this is an accumulative step change, remember, so I'm just comparing against the last step that we got to. So on the last step, which was NatHERS 7.5 star, essentially, we're now reducing again 10% the heating demands, which again, Melbourne is a heating dominated climate, so that's why we're looking at these. And I should say that, the base case building is in Melbourne, just for those of you who are elsewhere around the world. Moving on to the linear thermal bridges, we're seeing a 26% reduction from that base case, which is, again, it's significant. This is a big gap in compliance methodology. We could be saving a lot more energy if we started considering these things. So in total, from code to where we are now in this step, we've reduced our energy demands by 46%, which is pretty good. Looking at ventilation. Now we always start with natural cross ventilation. That's imperative in all residential design, no matter if it's passive house or not. but it should be supported with mechanical ventilation with heat recovery. And this mechanical heat recovery ventilation should have a winter mode and a summer mode with a bypass. Now, there's some awesome presentations by the experts in this. Please do look for them in the program. I am not an expert on HRV, but I do know that it's really, really important, and I'll show you why in a moment. So looking at 7.5 star and 6 star, which is code, they don't include heat recovery ventilation, and they rely on occupants opening windows for ventilation and fresh air. So we're not actually sure what that indoor environmental quality is going to be like, really. It's a bit of a risk item. Whereas in a passive house, you do have that, that control, that constant ventilation, and because it's commissioned, you have almost certainty that you'll have good air quality in that building. The reason why we always bang on about heat recovery ventilation. I'm sure everyone, you know, outside the passive house circles are fed up of us doing it, but it's so imperative for our health. We're in a pandemic at the moment, and this is more vital than ever before. We're spending more time inside. I know I am in Melbourne. We were apparently spending 90% inside, 90% of our time inside before this. Now, I'd hate to think about what it is now, probably more like, you know, 99.9% of our time inside. But this is why air quality is so important. You know, when unfavorable conditions exist outside, are we going to want to open our window if it's freezing cold or it's smoky or whatever is happening? We need to be sure that we can get fresh air without having to open a window. We also need to be sure that it's not being recirculated everywhere and that we're breathing in, you know, something that someone else has. Also, controlling the relative humidity is incredibly important. If we go outside the bracket of 40 to 60% relative humidity, try to say that really fast, you'll encounter things like respiratory issues. Again, don't want them at the moment. Or things like increased risk of bacteria, airborne viruses and bacteria. So really, we need to get on top of the ventilation of our buildings, and this is a very good way to do it. So the performance uplift of mechanical heat recovery ventilation, again, a really hard thing to say really fast, about 10%. Now, you know, I guess that this depends on a lot of aspects. It depends on air tightness as well, which we are going to explore next. But that's still a pretty good leap in performance uplift. And now we're at 56% improvement on code. So we're really making good headway here. So as I say, air tightness, and I have put them in that order because I know the saying is, build tight, ventilate right, but really I think it should be ventilate right, build tight, because you shouldn't have an airtight building without the ventilation system. The ventilation comes first, full stop. Again, there will be presentations exploring that one a little bit in more detail as well, so please do look out for those great presentations in the program. Air tightness, we're looking not only at the building envelope, but we're looking at the openings, the windows and doors, really, really critical. We need to make them airtight as well. We're also looking at, you know, vapor control. You shouldn't have an airtight building without vapor control. This is really important. We don't want to wrap our building in a plastic bag. Again, awesome presentations on specifically this element, so please do look at the program. External wrap requirements should act as a sort of Gore-Tex jacket to your building. They should be vapor permeable so that they let moisture out of the fabric and not in. And likewise, the air tightness membrane on the inside should be vapor permeable as well, just to stop any buildup of moisture. It's really important to communicate the benefits of air tightness to clients. I think one that is often not covered is the acoustic performance that you will get from an airtight building. It's just so critical when we're talking about denser living scenarios like in multi-res. I know that there's been beautiful weather outside, and I've wanted to sleep with my door open or my window open, and my neighbors have been partying, and it's just yeah, it's incredibly annoying and frustrating to not be able to open your window. So air tightness is key. So the performance uplift of air tightness, we are looking at a baseline of 10 air changes per hour, remember. So this is why the leap is quite big. So it's 23% improvement on our last step to get down to 0.6 air changes. Obviously, if you start with a base case of maybe 5 air changes, you're looking at a lower improvement, but this is sort of a good indication of what could be achieved from code. And now we're at almost 80% improvement on code just by doing those few things. So it's not hard, but it does take some prior preparation and planning. So what about other construction types? We've explored concrete and steel. What about some other options? So I was really fascinated to see what this concrete construction, how it would perform with timber studs. Now, some of you may know I used to work at Arkit, and I've also worked on other mass timber projects before. And so timber has been a really, really fundamental building material in the buildings that I've designed. And I'm really heartened by the fact that it actually, it is the winner because look at this performance uplift. Now, again, if you're a PHPP user, this won't surprise you, but it's really important to just show this on a graph and show what big performance uplift you can achieve just by introducing timber instead of steel studs. So we've already sort of halved our energy, our heating demand anyway, just in step 1. And you'll also find that the repeating thermal bridges are no longer an issue. So you won't need to increase your wall buildup. So we can achieve an 83% uplift on performance, which is better than what I just showed, which was 79%, just by swapping out the timber studs. Now, a lot of you will say, but you know, lightweight timber isn't what we use in multi-res. So that's okay, I've got you covered. I'm going to explore the steel stud option. And I'm going to explore something as well with CLT, because that is obviously a material that is growing in popularity, and rightly so. And this combination is quite common, I would say now. So steel facade system, CLT structure. Ah, that's interesting. You would have thought that we would be, you know, much better off from the start than perhaps the business as usual. But we're actually not that much better, only by a few kilowatt hours. So why is this? Well, you'll notice here that the repeating thermal bridges is a big step. So one could deduce that this is the steel's fault. So, I mean, we still improve the performance on code once we get to Passive House by 82%, which is good, but we're going to have to try quite hard to get there. We're going to have to reduce a lot of these thermal bridges and, yeah, I guess end up with a thicker wall system. So what about CLT and lightweight timber, just to throw it out there? Ah, interesting. We've jumped back down again. So it definitely is the steel studs that's causing us these issues. And again, this will get us, you know, halfway there, and we don't have to do too much else other than to add mechanical ventilation in and deal with our air tightness. That's pretty simple, right? What about CLT and CLT? So using CLT for the structure and CLT for the facade. Now, that is, again, it's more common than perhaps lightweight timber in a multi-residential building, but how does it stack up? Well, it's actually very similar to lightweight timber. In fact, it's exactly the same, providing you're giving the building the same values around the envelope. So, yeah, timber is the winner. So in conclusion, we want to just compare them all, obviously, see them in the same graph. And again, it does confirm that steel studs are are a massive hindrance to our performance. And they are the culprit of the, not making as much headway at the very beginning. So mitigation of thermal bridges is also pretty important along this step journey, and obviously that is more critical for steel and concrete. Mechanical heat recovery ventilation is really important and can almost get you to passive house level when you're using timber, but it is the air tightness that will get you all the way. So that is a critical step for achieving passive house compliance anyway, but also the performance levels of the 15 kilowatt hours per square meter for heating demand. How does it compare to code? Well, again, we're looking at, two different softwares here, and the pink is the compliance software, and you can see that this is where our gap is. We're not considering the same things. And there is such a big jump in performance when you start considering thermal bridges, air tightness, mechanical heat recovery ventilation, thermal bridges of all kinds. It's just so important to consider these things. Otherwise, you really aren't getting what you think you are. But don't rely on the graphs. Make sure you verify it as well. So blower door testing, go full certification. It is your quality assurance method, and it will give you peace of mind that what the graph says is what you will get. Also, don't forget other initiatives too. Passive House does these things really well. It does emissions well. It reduces energy. It improves indoor environmental quality, and it's a good way to innovate and push the industry to transform its ways towards net zero buildings. But we just shouldn't forget about the other really important aspects of sustainability, renewable energy, water management, sustainable transport, waste management, ecology and biodiversity, all of those things and more. So let's make sure we incorporate everything into a really holistic, deeply sustainable building, and hopefully regenerative building as well. So my parting advice, like through this whole pandemic, we just have to stay calm, keep calm, and mind the performance gap. Thank you very much, and I hope you enjoyed the presentation. And please do continue to ask me questions in the networking session this evening. Thank you.